Good morning, everyone. Welcome back to the last day of talks for the International Mission to Mars Design Competition. Today we have Adrian Brown. Dr. Adrian Brown is currently working as a planetary science researcher at the NASA headquarters in Washington, D.C. Adrian has a background in computer science and electrical engineering. His first degree was in electrical engineering from the Australian Defence Force Academy in Canberra, Australia. Adrian is a certified Java programmer. He completed his PhD in Earth and Planetary Science at Macquarie University in Sydney, Australia. And today he will be speaking about the Perseverance rover, formerly known as Mars 2020. Dr. Brown, you have the floor, and thank you so much for being here.
Thanks very much, Nicole. Just let me know if I start to drop out on you or anything, or the connection's not so great. I can always swap to a better Wi-Fi position in the house if necessary.
This looks good.
Great. Okay, so yes, so Mars 2020, the story so far, we're going to talk through a little bit about the mission. I'm not going to assume too much about what you know so far, but probably for some of you who are Marsophiles, and who isn't really, you probably know a little bit. So some of this may be redundant information, but hopefully I'm at least giving it to you with an Australian accent, which you don't get every day. So yeah, let's just jump at that. And just as a verification of the Australianness of my background, we've got the boxing kangaroo down there in the bottom right-hand corner. So everything's going to be perfect. Right. First, I want to start with a little pumping up video. So this is going to play automatically.
Are you seeing the video? We're not seeing the video.
All right. And just to check, were you able to hear that video? Because I'm going to play a couple more videos with noise. So if you weren't, then
we didn't hear it or see it.
Oh, you didn't see it. Oh, okay.
Is it on a different browser page, or is it in if it's
no, that's okay.
Okay.
Yeah, I'll just talk through it. So it was basically a sequence where the Martian, the future Martians from a scene from The Expanse, the series The Expanse, and it was when they were dropping their troops onto Phoebe to take it back from those dirty Earthers. So that's meant to be the pump up section, but and Neil just have to accept a little bit about Mars from today's viewpoint, shall we say. So we're not able to do any dropping around the solar system just yet, but who knows, in our future it may be there. Okay, so Mars 2020. Let's talk about the rover, the mission, and the landing site firstly. My background is in geology, so I'm very interested in all things geological and geophysical. So you might want to concentrate your questions on those lines when we come to the question time. And this is our launch from the Cape back in 2020, July 30th, 2020. It was a magnificent launch. Can you see it okay?
Yeah, I think your slides, is this all on your slideshow? Because it's not moving forward on our end.
Yeah, let me.
Oh, here it goes.
All right, let me.
Okay.
Okay, so now you're seeing it?
Yes, it's just not in presenter mode.
We could watch the video. It's fun.
Okay.
Okay, seeing the slides now. Let's see if I advance that it's okay. Anything advancing for you guys?
It's not advancing now. It's the original. Oh, there it is. Now it's advancing.
Interesting. Seem to be sharing. Okay, I'll just show it in presenter mode and see how good we can make it. Okay. All right. So let's go down here. Okay. So you can now see the first couple of slides and so on. Yep.
Yes.
Okay. All right. So let's talk firstly about Mars 2020 rover here. And now you can see the launch in the Cape. Be able to zoom in a little bit. Okay, almost good. Let's proceed to our next slide here. Okay, so you're seeing that slide menu. That's our en route to Mars slide.
Yeah, looks
okay.
Good.
Great. So this was captured just before we have a planetary science has division at NASA where I work has this Eyes on the Solar System app, and you can see where everything is. So this was taken a couple of days before we actually entered the Martian atmosphere and went into our landing sequence. And let me see if this is going to play.
Looks good.
And can you hear anything?
No.
All right. Okay, so this is the landing here, and now in this sequence, you should be able to see down the bottom, we'll have the parachute coming out, and the descent imager will be turning on there. Okay, so we're seeing the real video that was fed back from our EL cameras, that's the Adrian and landing cameras, and this is the first shots that we had of Mars. You can see our some of our descent equipment has gone down to the surface here, and we'll show you a couple of images of how that actually ended up on the surface, because we did investigate where it went. So we're landing in this delta feature. You can't see the delta at the moment. You'll get a little bit of a look at the side of the delta. What will happen is the images will start to lock up on a spot. And basically, that means that the engines have ignited and it's no longer floating by parachute. So you can see we're still just taking off the parachute right now. And the feature that you see on the right of the screen down here is the delta. So we wanted to, ideally, we wanted to land next to or on top of the delta. But what happened was during the sequence, the navigation camera and computer decided that it felt that it was going to land in these areas that were verboten areas. So they decided to move us away from our original planned landing spot, and you'll be able to see that move take place. So we actually end up not moving here, not landing right here where we're looking now next to the delta, but unfortunately we moved, or fortunately we moved across this dune field that you just saw scrape across the screen. And then the rover determined that it was happy to land in this area just off to the south of the dune field. So that actually, it was a lucky or unlucky happenstance, because we actually learned a lot more about the rocks that we were close to that we knew were going to be fascinating. And you can see the engines. The engines don't actually light up, but they make a whole lot of dust disappear from underneath our surfaces. And you can see these stunning images, which I always have to see as the rover. You'll see at the top, you can see the rover looking up, and the bottom is that entry and landing chassis looking down. And then that flies away safely. And then the best thing ever, really, is as demonstrated by these seals jumping around. Very excited. That was a very big day. So yes, this is the landing site. So I'll just show you this video here. So basically, the landing site is between two big beaches called Isidis Planitia here and the Syrtis Major here. So the Syrtis Major is a flat shield volcano. Syrtis Major is a big impact basin, and Jezero is sort of between them. Jezero is about 45 kilometers across. This crater here, which we call Belva crater, is about 1 kilometer across. You can ignore the line. It's basically a sort of semi-plan of how we might have got out of the crater. In fact, we couldn't actually take this path because this goes through those dune fields, but instead we've sort of gone around here and around here, and we're up over the top of Belva crater at the moment, as we'll see in just a second anyway. But so this was some thinking. If we had landed here, we might have gone across there, but that didn't come to pass. You can see this delta feature here, and the delta feature is what drew us to this crater, because here on Earth we know that wherever you see deltas, you also see water. So we're looking for the water that formed this delta, and so that's really the driving action behind our geological surveys of the area, and answering questions like how long was the water around for, and why was it preserved, and what else happened by the side of it. Can we get an idea of what was laid down before and after the delta as well, and why the water disappeared. So that's a couple of key questions that just spring to anybody's mind. We don't actually have answers to those questions, but if I can give you some unwarranted speculation, no doubt. Okay, so this we had actually seen this image as part of the sequence, but this is just another fantastic EDL single camera image from Sol 1. We number our sols day by day, so they're Martian days that we keep track of, and so you'll see me reference different sols. That's just what Martian day we are in the mission. That shows here, and that the green dot is where our landing point is, and this is what we looked like on the field. So we started taking photos of this landing site. It's called Octavia Butler Landing Site, after the science fiction author. And this one shows you also the scour marks, which you can see where we kicked up a lot of that dust as well. And so we're quite interested to see whether we'd exposed much in the way of rocks as we look back and grab these images here. But I also love this image because it shows off in the distance some tantalizing points, and I've just labeled a couple of them here. This, what we call butte or mesa, which might be familiar to some people in the West. This is part of the Delta system, actually, as we found. We didn't know it as we were looking at it, but we call it Kodiak. And it became the first it became the subject of the first science paper from a mission because it has huge boulders in it, meter-sized boulders in it that we weren't aware of the intensity of the waters that flowed through this to produce meter-sized boulders at this distance from the inlet channel, which is just over here. And then there's also you can see these rims in this mountain in the distance is the crater rim, about 10 kilometers from us at this point. And we also see some of these low-lying areas in the middle distance here. They're the delta deposits that we're also going to explore. So this is just a lovely image to show you what we were doing at this time, and also what's driven the missions then. Okay. Let's talk about some of these amazing images. So most of you will be aware that we also have on board us a helicopter called Ingenuity, and it took these amazing images of our anti-descent and landing gear. As I mentioned, it was all shiny when it flew away to Mars, and now it's ended up on the surface here, looking a lot like the ruins of the Titanic, with the parachute behind it as well. So in that, and this is these images came from Sol 218 of the mission. We're now at about Sol 790 now. And this, we also took a lot of debris photos. So this one here is the part of the EDL descent stage. So we're really making a lot of mess. This has got caught itself into this rock here, which is part of the Delta system too. So yeah, we're making a lot of mess around on the surface. This is one of my favorite recent images, for those of you who haven't seen this. So this is really a where's Wally for the hello, for the helo. This should be helo. This happened in Sol 772, and that we you can see any of the images that have these this type of cylindrical obstruction here. That's they're all going to be things taken from the cameras of the helicopter, and you can see my mouse, right? I'm not just yeah, I'll assume you can see my mouse, and if you can't, you can complain. But here you can see the rover right here. So what was happening here is that the rover, this is the Belva crater that I mentioned at the start. This is the rover observing Belva crater. So that's 1 kilometer across crater. That's what it looks like from the surface. The rover is looking over the rim of the crater. We decided we didn't want to go into, because it was probably going to be too dangerous, and just it just looked like a big challenge to get around a lot of dunes in the middle of it, which are covering the surface up. But the helicopter is taking an image over the rover's shoulder, if you will. So yeah, that's one of my favorite images from the heli. I also mentioned that we've been picking up parts of the delta here, and you can see some of these rocks here. We're still arguing exactly what relationship they've had from the delta, because these are obviously layered rocks. We call this rock Betty's rock, and these come from on top of the delta, so they don't have any other rocks on top of them, but they're sort of capping rock, and they could be caused by the last vestiges of the delta sort of dying out over the top of a more active delta stage below the Betty's rock outcrop. And actually, so you can see that the Betty's rock, which is this one here, fell down from up here, so it sort of made its way down onto the surface where it's sitting now, and we checked it out very closely because we wanted to take a sample from it. Unfortunately, it was really hard to get to drill onto the surface. So instead, we selected another target. It's a flat target down here, and we called that Skinner's Ridge. So just here. So a very compelling sample was taken. You can see our drill core here and the drill tailings here. And actually, we always take an abrasion next to the core, so we can compare the core with some fresh surface. So just like any geologist needs to look at some fresh rocks, we can do that with we can get through all the dust by drilling in with our abrasion tool. And so we do that every time that we have a desire to do what we call in situ science, and that usually involves the instruments on the turret, on the arm of the rover. And you can see a couple of pictures here of those instruments. There's the drill pointing out here, and there's also here is in this white box here is the pixel instruments, so that can also be put down onto the surface and check out these. And every time we do take a drill whip and have the opportunity to, we always do take these pixels. That gives us a lot of high resolution images of the surface, and we also get an elemental abundance map of the surface as well. So it's very, very advanced, built at JPL, custom built for the rover. We also have a lot of we have the abrasion tool. We have the Sherlock tool as well, which is a Raman instrument that can map the surface in Raman, and we also get a lot of information from the Watson camera, which goes with the Sherlock and Watson, of course. Yeah, I mentioned this paper. This is our first paper, and this is just gives you an idea of what we did with the images. You can see that we've really got up close to this Kodiak feature that was pretty close to our landing. Eventually, we got up there and well, quite close up there to take these images and these amazing meter-sized boulders. And there's a little bit of layering to them too, and sometimes you can see that there's a little bit of grading to them, meaning that there's the biggest ones are in the bottom, and there's a little bit of a smaller grain size on top of that. That's not very strong in this image, but you know, there's a little bit of grading there. And so to propel these meter-sized boulders, because these have come from somewhere outside the crater through the crater inlet while the water's flowing. So this is with this information, which we weren't able to take from orbit, for example, we were able to then quantify a lot better the nature of the delta system and also the strength of the water that's flowed there in the past. This is our second science paper here. Just to take you through, this was one where we looked in those dune covered areas that we eventually called SATAR. So if I say SATAR, that's what I mean. It means in the dunes. So basically, we sampled that area with our proximity instruments, and we were able to find undeniable evidence here from these samples in here, for example, of igneous. This rock was igneous. That means it came from a volcanic lava flow. So in the past, we had a lava flow that formed these rocks here, which is very exciting. Okay, let's go down here. You guys are probably desperate to ask questions, so let's go down to the bottom. I'll tell you a little bit about my background here and why I'm on this mission is because I like to study ancient rocks. So this is an image taken from when I was flying over the Pilbara region, which is an area in northwestern Australia. And it has some of the oldest rocks. And in fact, we have stromatolites down the bottom of this sequence here. So we were just trying to take images of them from the air and trying to get an idea of whether we could detect some stromatolites, say, from helicopters. And we're actually nearing a very interesting phase of the mission where we're actually on our way out of the crater. And Ingenuity has just rejoined us after about 60 souls of not communicating with us because we've been busy doing other things. But Ingenuity might be able to help us explore the area just on the exit of the crater. This just shows you a little bit more. We have this EOS article that came out about using the Martian rocks for sample return on Mars. And so also, just want to mention before we get into questions is that we are the first mission in the Mars sample return mission. So basically, our mandate is to get the most compelling samples that we can. We've made a cache on the surface already. So we have 10 samples out in the cache. That's the initial cache that will be brought back if we have a issue with the rover. But if we don't have an issue with the rover will be just presenting the samples that we've currently got on board at the moment to the Mars Sample Return landing vehicle. So this just shows you how we get the samples back into the rover, and then we rotate them through, and then we document them. We take images of them to make sure that we've got enough sample, because a couple of times we have had issues with not getting enough sample. And if we don't have enough sample, we can reuse the tube, but we prefer to not reuse tubes because, but in this point, we'll also measure seal. The seal is actually, it says seal sample tube. That sounds so easy, but it's actually really tough because we have to seal it in such a way that it's now going to be safe enough that it's not going to transfer any of that material out if the tube gets dropped onto the surface, for example, which we have to drop it onto the surface for caching and stuff like that. So yeah, sealing is a challenge. It's yeah, it's a challenge. So this is our first 12 samples. This isn't going to show you all of them, but currently we're up at about sample 20. But this is where our first 12 were taken from. I mentioned those SATAR ones in Bracken Missile, so we saw some images of those, and then we've taken some here of the Delta front and also the Delta top as well to try and get an idea of what the ages might be at the base of the Delta, and then to get an idea of how the rocks have aged, how long the Delta system took to deposit. So using geochronology on these samples where we get them back into our labs, because the rover can't do geochronology. So when we get these back to Earth, we'll be able to constrain how long the water system was active for example. Okay. How about I just leave it on this slide here? And yes, you guys can transfer to question mode if you like. If is a good time, Nicole.
It's a perfect time, and the questions are coming in
oh, good.
a whole bunch. So Ahmed would like to know, how does NASA analyze images from the Perseverance rover? Is it through artificial intelligence and computer algorithms, or by human examination of all captured images?
Right, it's the latter, I'm afraid. We don't use much artificial intelligence at the moment. We basically every sol that I mentioned, we have the sol, the Martian day, and so we plan every day of the Martian sol of the rover's life. So basically, as part of the plan, we have people who are looking at the images from the previous day and working out where the best place is to take the next image and so on. So when we get the images back, if they were in the previous, if they were on duty for the previous day and the previous sol, and put in the order for the images, then they can look at the image the next day. So basically, it takes about 24 hours for the images to get back if they're bad, if roughly anyway, if everything is going smoothly. Quite often it's not, because we have to deal with a pipeline, which is the Deep Space Network, and sometimes we don't have the Deep Space Network to ourselves. For example, when the Artemis mission was going through its testing, we got cut off from the Deep Space Network, and sometimes also we would go into conjunction, which is when the sun moves in front of the Mars from the Earth. So that happens roughly every 18 months or so. Our next one is going to be in November, so we have a couple of weeks off then. But other than that, we try to keep the rover working as as hard as we do here, and we individually look at every image essentially that we collect. Yeah, there are a lot of images that are also taken by the rover just for the rover's purposes. For example, the rover has a automatic ability to drive automatically. So I guess I should have mentioned that as well. That's not well, I'm not jumping to say that that's artificial intelligence, but it's a form of autonomy that's highly advanced in terms of Mars rovers, because we're actually able to travel. Essentially, you can point and click on for the rover planners. It usually doesn't work out, but the rover will send back questions if it reaches, say, a dune that's impassable or somewhere that it didn't feel that confident enough to get through by itself. And then we can tell it where to, to go around an object that's in its way. And then actually we've set records almost up to about a kilometer driving. And that's, pretty cool.
That is very cool. I love that it has a brain, right?
Oh, yeah.
And then there's a couple of questions about the sample return. So I'll ask them one at a time. Ahmed also wants to know, when will the samples be taken from the surface of Mars reach Earth? When, how, when and how? And then I have a couple of other questions about the same subject.
Okay. So I do have another slide on this, but probably take me too long to find it. So I'll just try and answer the. So at the moment, where Mars sample return, which is the second and third elements of the Mars sample return, that will involve the launching of a vehicle that's going to get onto the surface, and then it has to ascend off the vehicle as well. Sorry, ascend off the surface as well. So that has to launch to Mars first before we can get any of the samples back. So at the moment, the launch date for that is 2028. We can't launch every year because Mars comes into opposition with the Earth only every roughly 18 months. So basically we have a restriction in that. And then, so 2028 will be the best opportunity and allows us to work on the development of the most critical items, which first among which is the Mars Ascent rocket. So that's something that we haven't done before on another planet. So but then that process of collecting the samples should be relatively quick. So we'll probably if we hand over 30 samples, maybe it'll take a month or so to get them all across. And then the rover can go on its way, and then the Mars Ascent vehicle can also go on its way back to Earth. So, in theory, that should happen in the couple of years after 2028. But given the complexity of that mission, I think delays, it's not unreasonable to think there may be delays in the mission. And at the moment, it's what we call phase 3. So it's still, it's got the major design elements all done. But there are some things that need to be fleshed out still. We have, for example, gone to a simpler sample collection design. So initially, ESA was supplying the sample collection rover, and then we had to change from that because to cut down the costs. We didn't want to send too many things down to the surface. So instead, we put in a couple of helicopters. Given how well that Ingenuity has been doing, we decided to put a couple of sample helicopters. So in the event that we're not that the rover is not able to hand over the samples, then we're not able, then we can use these helicopters to do that instead. They have a gripping arm as well, so they're not quite the same as Ingenuity. They have a gripping arm, and they'll probably have some more advanced cameras as well. Yeah, and they have a ability to move about as well. So they have a ability to rove. They'll have small wheels they can rove with as well.
So I have a question because I wasn't, I'm just not sure. So is the cache for the samples, they're not all kept together? They're just dumped in separate places and the rover has to go find all of them? Is that what's happening?
Yeah, so the rover has currently on board, all the rest of the samples are going to be in the rover and taken by the rover. And then the sample, what we've done is if the rover has a problem, we've got this backup cache that I mentioned. That's the first 10 samples that we drop down onto the cache. In my screen, around this point here, which we called Tree Forks, in an area that's pretty flat. You can see it's relatively flat in this image too. So that's going to help the collection process as well. So essentially we have that's a backup plan in case the rover doesn't make it through. And if you want to, if you want to know the latest information on that particular thing, is that if we can send off sample return and until about 6 months into its journey to Mars, we can actually do a maneuver to choose between going somewhere outside the crater where the rover will be, or into the crater where the initial samples cache was set up. I know there are so many contingencies in this, it's very confusing just getting it out. It's sometimes a struggle.
It's complicated.
It is.
Planetary science and exploration is not easy. It's complicated. That's
right.
why it's such a wonderful project for these students to work on.
Yes.
Alex would like to know, how large are the samples taken?
Right. So they're about the size of a finger, about 5 centimeters long, and about this cylindrical size. So sometimes you might think that's too small, for example, but we are getting 30 of these samples at least that we'll get back, unless we collect the cache, which is only the 10 samples. But we expect to collect 30 of these 5 centimeter long rock samples. And you might think that's small, but that's actually, when we're doing our sample return analysis here on Earth, we'll be using a lot of non-destructive technology to look at these things, so such as X-rays and stuff like that, and also be doing very thin slices of the samples to some destructive methods, but mostly it'll be very non-destructive techniques that we'll be taking. And I haven't even mentioned the fact that we're actually also, and this builds a lot of into this increased cost, is that we have to make sure that there's nothing that's going to contaminate the Earth. So we have what we call a break the chain moment. So we have the samples housed in their own little container inside the return to Earth vehicle, which also increases the complexity quite a lot. And I've just said quite a lot. You can imagine that's months, years of work that goes into those sort of procedures for those engineers. I don't want to brush over that.
Yeah, it seems like it's going to be a long time, but it really is very important to plan it correctly. What are the scientists looking for when they get the samples back to Earth? Everything goes well, we presume, we hope. What are they looking for in the samples?
Right. So primarily, the first thing in any of these samples that we'd be looking for is any signs of life. So any signs, for example, unusual organics, for example, that we can't detect on the rover. So we have some indications of organics on the rover, on the samples, but we're not able to fully characterize them. So, and then they could be more advanced sort of technologies that we can turn on these samples when we get them back to Earth as well. We'll be able to date each of these, and so when I say date, that's become really practice art now. So we have the ability to essentially date any point on crystals. So some of these, you can see some of the crystals in here, like these are probably feldsite crystals, maybe here, and up in alfalfa, for example, there's some olivine crystals as well. So we're actually able to date individual layers in the crystals as well. So, and in particular, if they've got any zircons or anything like that, we can do that dating as well. So when we get the delta samples, which are these Thornton Gap, Swift Run, Skyland, Bear Wallow, Hazeltop, Berry Hollow, those sort of samples, you can also see that they're very fine grained. So we'll be able to put them under the microscope, put on the electron microscope, put them under the string microscope, detect any strings by that time. I'm sure we'll detect string theory as well by that time. So yeah.
Okay, and
at high resolution. Yeah.
Sorry, your signal was cutting out. I thought you were done talking. Sorry, I didn't mean to talk over you. I apologize.
No, that's okay.
So on the sample return, now that we know they're looking for signs of life and be able to do, different types of research, how can we guarantee they are not contaminated from landing on Earth?
Mm-hmm. Yes, that's another part of it. I did talk about, or I mentioned the fact that we're breaking the chain from Mars that happens in orbit around Mars, and then when we get to back to Earth, we also have to take care that this doesn't just end up on the desert floor in Utah, for example, like the solar samples did. So we also have to take care that we're not forward contaminating the Earth with Martian microbes, for example. So what we're doing is NASA is now building a new building to house these samples. It'll be a Category 5 containment facility. So things like positive pressure and negative pressure at various parts of this building. We'll have a top range instrumentation on board as well. So these will do the initial assessments for, in particular, for biosignatures and for organics and those sort of things that could affect life here on Earth. So and nullifying that opportunity, essentially like the lunar sample did when they came back from the Apollo missions. So we'll be taking those sort of precautions and more, because Mars is more likely than the Moon to have started some biological activity. So essentially, after that processes have been carried out, maybe after a year or so, the scientists have looked over these things and think that they understand them enough to release them to other scientific analyses around the world, for example, because this will be very much an international mission as well. We have participation from ESA, so they will be wanting to see these samples in Europe as well, for example. So and then we'll also want to compare them with other labs around the world as well, and use their state-of-the-art equipment as well.
Okay, there's two more questions that just came in, and our next speaker is in the queue, so feel free to make these as quick as possible, so for time's sake.
I could talk for hours.
I know, so could I. Angela would like to know, could you talk about the terrain relative navigation process?
Sure. So yeah, the terrain element, yes, I think that you're referring to the ability to descend onto the surface and land. so yes, that was carried out by our entry, descent, and landing people. So essentially, they had a map that we wanted to land just in here into the delta, in next to the delta. And as you saw in that entry, descent, landing video, it looked like we were going to land in here in this dune covered area, just here. And so instead they sent us out here where we landed basically about here. So that was all guided by the terrain relative navigation, TRN. And essentially what the TRN allowed us to do was compensate for any difficulties encountered by the rover independently. So in previous missions, they've had like 20-kilometer size ellipses that we had to make as flat as possible. And so that's why we ended up in some really flat terrain for the previous Mars missions, such as Spirit and Opportunity. They were in very flat terrain. We were able to land in some very challenging terrain, as you can see. There's these areas here, that, so we're looking at Belva Crater here is about a kilometer across. So a 20-kilometer ellipse would encompass this image plus more. So that's obviously not flat enough for Spirit and Opportunity. But with the terrain relative navigation built in, we were able to make a confident call that we were going to get down to the surface in a safe spot. And in fact, did work and sent us away from the delta, away from the dune areas, which essentially were deemed as unnavigable before the mission.
Wonderful.
I hope that dealt with that question.
And Tissia would like to know, when scientists analyze these samples, does the sample ever happen to trigger a reaction in humans, like an allergy, which I think is probably the most important thing for a human mission to Mars to know ahead of time?
Yeah, absolutely. And you can see these samples that you can see, they essentially look pretty much like rocky samples, but as I mentioned, we'll be looking for these organics on top of these surfaces. So there will be organics that we find in these rocks that we're not able to find with the rover. Anything that's going to harm us comes into that organics category. So if we find that there's little to no organic background, that will give us more confidence that we'll be able to proceed and hand out these samples outside of our sample return facility. So we won't be sending them outside of the sample return facility until that check for organics is complete. And obviously that will be a very big bureaucratic sort of step to sign off on. Probably the president will sign off on letting these samples out. Joe Biden, I'm sure, will still be around with us, of course.
Awesome. Wonderful. I hope that is true.
Yeah.
Dr. Brown, so much appreciation and gratitude to you for spending your time with us today. And this video will be uploaded in the next couple of days to the YouTube channel. So feel free to share this with whoever you like. And I really appreciate you being here. Feel free to stay for the next talk. Students, we have Susan Jewell. She will be speaking next. Susan is a space medicine physician, scientist, analog astronaut, and exponential technologist, entrepreneur, and a space coach for AFWork, empowered by USA Space Force and US Air Force. Today we will, let's see, Dr. Brown, if you could unshare so Susan can share her screen. Today, Susan Jewell will be talking about space medicine and cybernetics, telepresence, humanoid, telerobotics, and avatars. So this is the fun stuff. Okay, welcome, and
Thank
you have
you.
the floor.
Thank you so much. I know that was a mouthful. That's a really long title.
It was beautiful. It was beautiful.
Thank you so much, Nicole, for that wonderful introduction. And Hello, everybody. It's a pleasure to be here. And from geology, we're going to go to technology. And so, yes, I've been in the field of frontier, we call frontier technology, or there's another word they coin, exponential technology. And how do you apply that for enabling humanity to actually thrive in space, settle in space, and also austere environments on Earth? So with that said, these are my two organizations that we're heavily involved in bringing and testing, doing research and development in all fields of the acronym for STEAM, right? To be able to develop these products, technology, procedures, whatever it is that we need, but you need to do scientific research and then to be able to validate and proof of concept and then apply it in the environment that you want. So with that said, let's move on to the next slide. So yes, today my talk is entitled Cybernetic Telepresence Humanoid Avatars. And the applications, I'll give you some examples of how we can apply some of these early innovations that we are working on for changing the paradigm for space exploration, of course, to change the way that we conduct healthcare on Earth, and how can that also be translated for space, for celestial settlements where we go back to the moon and Mars, definitely for education and entertainment, which I'm sure most of you have worked, or maybe some of you have not experienced virtual reality and then been entertained, in that arena, in a virtual world. Or if you're a gamer, that's a form of, using these avatars in a certain way to entertain yourself. So I'm just wondering why I can't move forward. Oh, there we go. Now, so the idea of cybernetic avatars is not new. In fact, the leading country that is developing these capabilities is Japan. Japan is heavily involved in innovation and bringing in robotics into our daily lives. So they literally, the government of Japan is working on this moonshot goal to bring avatars, in this case, cybernetic avatars, into life as part of your life. And their goal is, how can they conduct and they perform and develop the idea, the moonshot goal of the realization of building a future society. And of course, you can extrapolate this to the space, right? The moon society, the Martian society in the future, but the realization of a society in which human beings are free of limitations of our own physical body, our brain, the space that we live in. And they want to be able to say, by 2050, we will have the capability in integrating all these sort of technologies, right? Robotics, avatars, telepresence, into all these other aspects of our lives here on Earth and in on the future, maybe living on Mars. And so here, obviously, they've given you, this is sort of their top level visual diagram of how you can apply these cybernetic avatars into interacting in disaster relief, in the sports, and health and creative ways as well. So this is really interesting, giving you as a way, as a sort of introduction, that this is not a new concept. It's been there over the last decade, and it's just hasn't been adopted on a global basis. But we're expanding this because now the technology of immersion, using spatial computing, which you all know is the HoloLens, or it's the Apple just released a augmented reality headset, the capability of us going into the so-called metaverse, right, as avatars and interacting with each other, interacting with the simulated world is now a feasible way to do this. So with that, there is actually, this is really interesting because there's this organization called 2045. They've been, online for over a decade, but this is their sort of projection milestone of how they see this whole idea of us being integrated into avatars or interacting with avatars. And this is sort of, obviously it's not it's going to set in stone, but it gives you some kind of their sort of vision and some timeline milestones of where they see the technology and where we will actually move forward. So, 2040, 2045, maybe we will have the ability to have our own holographic like avatars. Well, we already have that. There are platforms and software where you can create your own avatars, where you can create really lifelike avatars that you can interact with, or one that represents you. So even now, today at 2023, their capability of hologram avatars of self or others, or interacting with others is already a possibility. And then the other, they're saying, okay, then taking it more evolved to be able to interact, having artificial brains, be able to transfer a personality or consciousness into the avatars. That's kind of where there's some elements of that happening. And in a minute, I'll show you, for example, what Neuralink is doing, which is formed by Elon Musk, right? If you don't know Elon Musk, you should Google him. But he's the CEO of SpaceX. So, but he also is thinking of how you can interact, upload your brain onto the internet, right? And that's where the Neuralink capability is. And that's just an example. Anyway, I won't go into too much of this slide, but this is interesting because this organization has been there online, for the last decade or so. And when we look at where we are now, with the technologies, all this being written out as a milestone vision is actually coming into manifestation. Okay. I don't know why I can't go forward. And so here we go. The very first, and this is very, like every time we develop a technology, it's going to start very crude, right? But look where we are now. There are companies, and there's Tesla. Tesla is Elon Musk's company. He's building the, electric cars, but he's also creating the humanoid robots. So these, and this was just recently shown when they did their sort of, a shareholder meeting, and they showed a group of their humanoid robots that were moving together. And the idea is you can have yourself interact, with the humanoid robot, or you can be in the humanoid robot, teleportation, quote unquote, to be able to then interact with your environment. That latter is what we're working on. Not so much as the humanoid robot itself being an independent, autonomous robot, which is where they're heading. But we're talking about cybernetic, where you're able to transport your humanoid sensorium into a robot format, and it doesn't have to be humanoid like this. In a minute, I'll show you our flying drone cybernetic humanoid robot, teleavatar robot. So it's the ability for sort of integrating your humanoid sensorium using all these senses and these headsets to be able to interact with that environment that you're not physically present, but you can teleport yourself there, your sensorium there, and interact in real time. So here we are, the Neuralink, right? Here it's really interesting is what they want to do. This is the very first step of integrating the human brain and uploading our brain interface with a computer, right? So that's what this company is, and there are other companies or other groups are doing this, right? But the whole idea of, in the future, and not too distant future, we will literally have, our ability to interface with each other from, using our brain. We don't have to be physically there, but interact with each other, because of this capability. And I'm not going to go into too much of this, but what's so interesting is the fact that this Neuralink chip, you can see here on the right, these are chips that are implanted. They're a very, very small scale, kind of nano scale or even pico scale, right? 10 to the minus 12, it's thinner than the shaft of a hair. And you can implant these chips at certain aspects of your brain cortex that controls certain motor function or sensory function, and you're able to stimulate that area to perform whatever you want. So in this case, what's so interesting, their first case is they got the FDA approval, which is an enormous achievement for the first human trials that's going to happen later this year or early next year for paralyzed patients. In other words, they're able to say, can we use these brain chips, right, that will then allow a paralyzed patient to have motor capabilities that they didn't have before, right? So this is very early, but think about when it matures, say in the next decade, in the next 20 years, it wouldn't just be for paralyzed patients. It would expand to healthy, quote unquote, patients, and maybe would use, I'm just saying, they could be able to enhance our capabilities. So this is really interesting, but it's back to this slide, right? Where we at, it's saying here 2030, 2035, you will be able to have the interface of your consciousness, your brain onto the internet, right? Which in the past was never a feasible possibility, but it is now. And then another interesting capability of brain interface control using technology is this company called OpenBCI. And they built this as a DIY. You can go to it, it's OpenBCI. You buy these kits and you can build these EEG headsets. But what they've shown recently was amazing, was this a paralyzed person that went on stage and they built this brain interface with this EEG headset, and this paralyzed person was able to fly a drone. You see the drone in the head here? To fly this drone just using his thoughts. That is an amazing achievement, to be able to use your thoughts, have these impulses that are, stimulated by this EEG headset, and then with your thought, be able to fly a drone. That is an example of where these technologies are moving forward. So with that, I want to show you what we're doing. That is another kind of concept of humanoid, cybernetic humanoid avatars. In this case, like I said, you don't need to have, a robot looking like that, right? It doesn't have to be human looking. Who says it has to be? Look, this one is not. It's actually, a headset, EEG headset, and flying an object, in this case a drone. In our case, our sort of robot is our hybrid drone and rover, and onboarded all these technologies, and here onboarded with telepresence avatars by using XR spatial computing, coming in, putting on, also integrating with digital twinning, and later on I'll show you proof of concept. We've actually been able to run a robotic arm using using the HoloLens, right? The spatial computing, how you can maneuver the robotic arm without actually physically there maneuvering it, and using virtual reality, or not virtual, augmented reality. But the idea is we brought on telemedicine capabilities, so you can interact real time with medical people, your surgeon, your doctor, or it doesn't even have to be medical. Of course, we're applying to medicine right now because that's our main focus. But in the future, maybe on Mars, you say, well, I need a professional plumber, an electrician, well, then they can teleport themselves in this sort of setting and be able to interact with you in real time and help you and support you. So I'm going to show you, hopefully this plays, the video of this concept, the Medinaut. And I forgot to, Nicole, I forgot to put on the video sound. So I think, because you won't be, can you hear this? I don't think. Can you hear that?
No.
No. So I think I need to stop and then stop sharing and come back in, but I have to share the sound and the audio. Oh, there we go. So I'll do it now. Sorry about that, everybody.
No problem. No problem.
Okay, now optimize video. It won't allow me to do that. So never mind. Okay. Now it should work. Should be able to hear. So tell me if you can hear the sound.
Avatar Medic.
Yes.
Medinaut drone. The Flying Da Vinci. Avatar Medic Medinaut drone will enable on-site medical providers and first responders to have access to next-generation life-saving interventions and training. Moreover, using the power of telementoring, the Avatar Medic drone can instruct and support non-medical persons to render accurate life-saving aid. Medinaut is capable of locating injured persons in remote environments, landing near, moving toward, and providing data stream of injured person's status. The Medinaut is controlled via mixed mode of direct operation and autonomous pathfinding. Wheels with motors within and four-wheel steering ability enable ground mobility. The drone features two snake-armed articulating end effectors for grabbing and precise cutting and suturing. The end effectors are designed to enable wide pressure for bleeding control and patient assessment, along with retractable laparoscopic end effectors, opening the possibility of suturing and basic surgical interventions. Modular storage bays, modular splint backboard system, and other medical intervention technologies enable the Avatar Medic drone to render effective aid in remote and austere environments.
Okay, so right now, we've been working on this. Why doesn't it let me go forward? It doesn't let me go forward. That's so strange. That's why you play videos and then it's like, it won't let me move my video forward. I mean, my presentation. Don't know how to do this. Here we go. There we go. Oh, no. All right. So with that, you say, well, that's really difficult. Well, right now we're very early building the prototype, and it's a matter is like anything that is hard to do. You have to work in a very multidisciplinary environment with lots of different people from different expertise areas, right? So that's kind of what we did. We created environment where we have experts in robotics, experts in XR, telemedicine, experts in, biosensors, haptics, and all this, and then coming together to solve this problem and build this. And that's kind of why, it's the feasibility of manifesting that vision will can be a possibility, right? And so right now we're also working with the government to be able to develop this capability, because it has advantages in terms of how do you get medical attention or intervention in real time in a battlefield or in a disaster area, right? Where there is no access to resources, to supplies, to medical experts, when you can't get the support there. And so using this capability where you can fly in, where you can do real-time intervention, at the injury site is now a possible reality. And then definitely for space, right? There is, at this point in time, we cannot do surgery in space. We can't really do medical intervention in space. And if we are thinking about living, on the surface of Moon and definitely on the surface of Mars, we've got to be able to say, can we actually help prevent, death? Can we help to interact when there's life-threatening injuries, right? And this is the capability. I think these capabilities, if we're able to really, be successful in developing it, it will, I'd say the answer would be yes, right? But we definitely need this before we can even venture out beyond low Earth orbit, and to say that we can be successful multiplanetary species. But this is also interesting because it involves a lot of areas of STEM, right? So definitely engineering, but it also needs the creative aspect team to come in and do this. So I think that, for us being part of the sort of future thinkers, the visionary, the pioneers, this is an exciting project per se. It's also ability to bring in younger next generation community students, citizen scientists who are interested not only in space but in the engineering aspect, in the visionary aspect of it, right? To come in and work together, right, to do this. So another aspect of being able to do that is the virtual digital twinning. And virtual twinning is a new but a very exciting area that is a platform technology that is using all these sort of exponential technologies, right? Using augmented reality, using robotics, simulation, using AI, artificial intelligence. It's really the definition of a virtual twin is when you build a simulated, replication of whatever it is you want, a model of whatever it is. So in our case, it's a robotic arm, but it could be the surface of the moon. You can build a virtual twin if you've got all the data, and we have the information about the geology of the moon or Mars, about the weather, about the conditions there, the environment. So it can be that kind of a virtual twin that you want to develop, and it's a computerized simulation of that twin that you want, and then you can do predictive analytics. You can put in caveats of problems and put those problem sets into that twin that you just created, and then it will be able to try to find some solutions for those particular problems, right? To help you make decisions, to help you foresee problems that you can mitigate or prevent. In this case, what we were trying to do was build a robotic arm. And in this case, you can see this robotic arm is all 3D printed. It's a very expensive robotic arm, so we're at $50,000 to $80,000 to buy one. And then what we wanted to do was to prove a concept of using, in this case, you could see a person wearing the HoloLens 2, which is a spatial computing XR headset, and say, can we do a virtual twin replica of this robotic arm, and then using the virtual controls, which I'll show you in a minute of the video, to maneuver the robotic arm and do the tasks or the maneuvers that you want the actual robotic arm to do, but you do it with a virtual arm first, right? The virtual twin of the robotic arm. And so in this case, we wanted to say, because at the end of the day, we want to say, we want to use the XR to do the tasks, remotely. And then that will be translated to the actual robotic arm. So at the end of our, when you remember the Medinaut, we got the robotic arms doing all the medical intervention, right? That's what we want to do, to be able to allow the surgeon or the doctor to be able to manipulate the robotic arm to do certain tasks, right? So with that, let's see if I could play the example, and then see I can explain to you. Well, I think you can visually also see what it's showing you. So here he's got the HoloLens 2, spatial computing, and he's got his hand out because he's looking at the virtual controls, which is on the surface of his hand, the palm here. All right, let's play this and see. So you could see there's the pointer because he's using the virtual. This is the virtual digital twin of the robotic arm. It picked up this brick and it maneuvered from A to B. And in a minute, you see his hand coming out, and he has on his hand superimposed the virtual controls. So he's just going to actually point to the virtual control. And then there's a certain latency right now. This is kind of, as half a second latency. And then it will translate the virtual arm movement to the actual robotic arm, and you could see the robotic arm doing exactly the same maneuver as the virtual arm, the virtual twin. So this was a proof of concept for us to apply digital twinning concept into our sort of Medinaut. But it's, in this case, I'm just showing you this particular example, but the digital twin can be used for many, many other situations, right, and applications. And this is a really exciting, especially for education, the future of education. It will change the ability for us to, immerse the student and the trainer into an immersive world to do the training in real time, right? And get to see a 360 of the environment or of the model of whatever it is, right? And then interact with it in real time together. So another area of cybernetic avatars is using avatars to do surgery, to do telesurgery, teleanesthesia in space. And if you don't know about analog astronautics, it's an expanding field. It's a simulation of actually, in our case, astronauts. They live and work together in crews, and they're deployed to these analog sites around the world, into these sort of habitats, right? And they live as though they're living on the surface of the moon or Mars. And then in that environment, or that experience learning, they get to learn about technology, they interact with the technology, they get to learn about human behavior, the challenges and the problems of working together in a small crew. So it's similar to the astronauts living on the International Space Station, but now we're saying we're going to have them as analog astronauts, because they're not literally in space. They're still under 1G on Earth. So that's why it's analog astronauts. But they want to be able to give the experience to the crew of what the challenges are like living on the surface of a planet. And so in this case, with our company Avatar Medic, over the years, we actually work with MRs to be able to deploy a lot of analog astronaut crew missions to austere environments. We went to Nepal, 15,000 feet. We'll be going underwater to the analog habitat of the Florida Keys in early 2024. But in this case, we worked on developing the medical technology for space medicine, right? Space medics, because in the future, we're definitely going to need a lot more medically trained space medics or space doctors when there are more people that will be foraying and living out in space, right? That's the commercial space sector, with Axiom Space, with Blue Origin's Orbital Reef. Other organizations are building these commercial space stations. And then, of course, the Artemis mission, with the future of building lunar settlements and then eventually Martian settlements. We can have, in the next decade or two, thousands of people living in space and working in space. And then the probability of accidents, of injuries is going to be there. So how do you take care of them? So this is the whole idea of building the avatars, this tele-robotic humanoid avatars, where now you can actually teleport the surgeon or the doctor to that environment, whether it's to microgravity on the commercial station, or to the surface of the moon, or to Mars. They don't need to literally have to be there in person. They teleport with these capabilities to interact. So you can see here where we have a crew, and they're there in this sort of analog habitat with space clinics, a prototyping, right? It's out in the desert of Mojave. It's designated as the space clinic, or the clinical area where they do all the medical training. And this is the crew. They're all non-medical. So the question was, can they acquire knowledge and skills, by being trained or tele-mentored by the remote medical team to do these particular basic life support intervention, basic, surgery, basic anesthesia, and using robotics. So in this case, we have the same robotic arm here, but this was controlled by a surgeon 300 miles away, because this was in Mojave, and from Las Vegas, the surgeon was able to maneuver the robotic arm remotely and work with the non-medical crew how to actually do intubation. So this was really interesting, and it's something that we've been working on over the years to be able to develop these capabilities, right? And develop the protocols and to train the non-medical team how to acquire this knowledge. But then you can see here, we're working with developing an actual humanoid robot, which was similar to the Tesla robot. But in this case, bringing in, the telepresence. So you could see, and I'll show you as our last part of the video, actual, interaction with a patient during a simple neurological exam, but it's the robot that's going into the physical environment, but the surgeon or the doctor coming in via telepresence, right, and talking. So this would have been, if this technology was more advanced a couple of years ago, we would have saved a lot of first responder or frontline medical healthcare professionals, because when the COVID hit, the pandemic, we didn't have the capabilities of these humanoid, robots that could go into the dangerous environments, in other words, patients with COVID, and then the surgeons can interact, or the doctors interact remotely, so they're not putting themselves at risk. We didn't have this capability a few years ago. So the result of that was hundreds of, thousands of frontline doctors and surgeons and nurses actually died. And so it was a huge problem. So, but it's never too late. Here we are at today, 2023, where the advancement of telerobotics and avatars has really matured to allow us to be able to build these capabilities. But like I said, it's not only for space here on Earth. This is a clinical setting in a hospital. It could be out for disaster, mitigation support. It could be here's, this image was created by DALI 2, the software, where there's an interaction with the students. Maybe here, the caveat could be the students are living on the surface of Mars or in a classroom. You have a robot, but you have a specialized expert coming in, just like I'm coming in talking to you via Zoom. But now the robot's interacting with you, but the person talking to you is an actual person, but living on Earth, right? Obviously, Mars, there's a latency. So let's just say, we overcame the latency, and the teacher's interacting with you in real time, but in this robotic presence. So let's then, I want to stop sharing this particular slide, and I'll show you this neurological exam of this robot with the doctor, with it says me, right? Talking and conducting a neurological exam with this patient. So I need to share another video if I can. I think give me a second, I need to find the video. All right, here we go. And then I think I will take some questions after I show you this video. Okay, so let me share this. Zoom forces you to do all these multiple steps. Okay.
It allows us to talk to you, and we're all far away from each other. So that's awesome.
I know, exactly. Okay, so let me share this last video. This is the simple neurological exam using the robot and the telepresence capability. In other words, the cybernetic avatar, humanoid avatar. Okay, so let's share. And can you see my screen now? Yes?
Yes.
All right, here we go.
Dr. Dewberry, and I'm here to take the neurology exam. I just need you to relax and just follow my instructions, okay? First thing I need you to do is to keep looking directly at my eyes and then follow my instructions. So this is the pen light, and I'm going to shine it into your eyes now. Okay, keep looking at me. That's great. That's right. Good. Now I'm going to shine the light in the other eye, but keep just looking directly at my eyes. Right? Okay? Wonderful. Hi, Dorian. So
All right. So, I mean, that was a short and quick, but it gives you a good example of the whole idea of, in that case, you have the doctor, coming in with inside the robot avatar, right? The doctor is the avatar, but it's telepresence, but the robot's physically there, and the humanoid sensorium of the doctor is there, but the physical presence of the doctor's not there. So in a dangerous environment, where there's patients have to be isolated because they have a virus that's contagious, you don't want the doctor to be there. You don't want the nurse to be there. They will put themselves at risk. So this is a way to do that. But you can extrapolate that into other austere environments or dangerous environments, space, right? Which is what we're talking about in the future. So the idea of the integration of the convergence of all these frontier technologies, right, is going to enable us to do this. And it's a really exciting time for us at this juncture of our humanity that will allow us to actually, because we don't just want to go to space and then, we're not tourists. I mean, there will be a sector where people just go and visit and be tourists and come back. But there's many of us who, like Elon Musk and Jeff Bezos, Blue Origin, want to build, humanity become multiplanetary and have permanence in space. And so we want to thrive there and not just live there, right? I mean, just go there and visit and come back. We don't just want to survive, we want to thrive. And that's important. So, all right, that's the end of my presentation. Open to questions.
Wonderful presentation. Thank you so much for sharing your knowledge and time with us. And I'm sure as these students are planning a human mission to Mars, medical information is very, very important, because inevitably something's going to happen to somebody when they're on Mars medically. Ahmed would like to know, how will this technology help with a delay of the 20-minute time to transmit the signal to Mars?
Yes, so that's what I said earlier. It's called latency, right? Latency is the delay in time of actual transmission to get to, you know, whatever it is that you want to get to, right? So that is a huge problem with the technology latency. But right now, you know, we're talking about 5G, you know, which is reduces that latency period, but also, you know, it's a challenge. We have to work on it. You know, there is research looking at 6G, but if we don't overcome the latency, I think that will always be a problem. So you have to say, okay, think out of the box. You're not going to transmit from Earth to Mars. You'll be on the moon, one of the moon of Mars, and so maybe your mission control will be there. Your medical team will be there. So therefore, that latency would not be a problem. The other scenario is actually having station to station on the surface of the planet, so the latency wouldn't be there. So you have to think out of the box.
And what I bet quantum computing, if we get that worked out, that might help the latency as well.
Absolutely. Yeah. A good question though, right?
Yes, of course. Andre would like to know, if it can be used in a wide variety of applications, what are the possibilities of the worst case scenario of digital twinning being used? Is there any risk for the user?
The risk of the user? No, because it's a virtual computation, computerized environment. That's why it's called a virtual digital twinning, right? Digital. So you're not physically there, right? That's the reason why we want to build these humanoid cybernetic robot avatars, because the robot will be there physically. So if there's an explosion or whatever, right? A mass, you know, radiation exposure, the robot is exposed, not the humans. The humans are so fragile. Like we did the drone, I showed you the drone rover, the Medinaut. It's the drone, you know, the physical, you know, drone and rover is going to be there in that environment. The presence, the humanoid presence of that human is there, but the physical molecular structure of our human present body is not there. So we're not subjected to all the environmental issues or catastrophe that's happening right there, right? So we don't get injured. Does that make sense?
Yes.
And that's the reason why it's needed, right? Because it doesn't make sense to, for example, when we have accidents, you know, like disasters, or, you know, or when even the astronauts doing moonwalk, it doesn't make sense to try to solve a problem by putting others in that same situation and put them at risk, right? Technology should enable us to mitigate that. And that's what this whole idea is, where the humans there, but they're not physically present, you know, their molecular structure is not there. So they won't be subjected to the threat, right? But they could still do the things that's needed, right? The interaction can be there in real time and they can perform the task, right? Because they're inside. It's kind of like putting yourself inside a robot, you know, a physical structure that you can manipulate and move, right? I mean, and that prevents you from putting yourself into danger. And that's always an important, right? Safety first.
Right. And Tissia would like to know, what if there is a malfunction in the humanoid robot, I presume she means, specifically if a surgery is going on?
Yeah, that's a very good question. But remember, anytime that you want to use technology, it matures over time, right? And so we're very early stage in this, trying to apply this into this setting. So like anything you do, it's called prototyping, iteration, validating, proving it over and over, so it becomes more more efficient and more mature, the technology, and the the reduction in the risk and the problems. But no system is ever 100% efficient, no system at all. So you just got to try the best you can by trying to mitigate and reduce as many of the risks and most problems. The way you do that is to keep doing iterations of it and finding out what the problems are and try to solve those problems, and you move on, you keep evolving and maturing it, right? And that's where we're going. So the good example is this, our cell phone, right? When we first started with communication centuries ago, we didn't have cell phones, right? We just had, was it I forget what they called, typing thing.
Telegram,
And then
the telegram.
yeah, exactly. And then it became the rotary phones, which I used that's how old I am. I use rotary phones, right? Dialing rotary. I mean, that is an example. Of course, it took a long time to get to the cell phone and where we're going now. We got the headsets and, the AR, XR headsets and where that's going, but at the end of the day, it's the sort of the reduction and the miniaturization of everything and the reduction of time to get to places, to get to communicate. That's what technology does, right? Always use example of coming out of the cave and where we are now, right? And our mobility and communication are two great examples. And you look back in history and where it's going, where we are now, how technology has enabled us to where we are now, and to then where we're going to go, right? So those are two good examples. So back to your question is, of course, we're not going to be doing surgery right now because we're not there yet. But that's kind of where the future, where we want, that's one of our target goals. So we'll work out to get to there. But the idea that we can teleport our humanoid sensorium with all these technologies at this point in time is an amazing achievement. That's what I would say. And we're looking for pioneers and visionaries and people, students who are interested in working in this field and being able to be part of this, because it's still very early innovation, right? Still very early pioneering work, so. And just like the cell phone was created under NASA for the early days of astronauts, the early human space flight for us, and they needed to communicate. They created, the cell phone communication, right? So, look where they started. When they did that, they had a whole room of computers, and it had less computation power than we have. But they're able to do that to land humans on the moon, right? If you believe that humans did land on the moon, which they did. So yes, that's our vision. That's our goal. We want to be able to do surgery in remote areas, overcome the challenges. Was the first question, latency? But there are, but like you say, Nicole, quantum computing, the ability, other new discoveries maybe we haven't found yet, that come into manifestation that will allow us to solve these problems. But it's better to do it, have a vision, start prototyping, pioneering it, and see where it goes, right?
Absolutely. Otherwise, we'd still be in the cave, right? If we weren't always innovating, we'd
Yes.
still be there. And
however, yes, it's true. But however, if you want to live in a cave, if you want to live underground and you have that experience as part of our analog missions, is to give you this real, what we call experiential learning. So we're actually going to be doing underwater aquanautics, so you can learn to live underwater in a habitat, or we actually do lava nauts, to go in the lava tubes and do missions there, and even in a cave. It's kind of cave-like, right? Cavenauts. The point is, there's a long word for that, I can never say it. Spelunking is cave divers. And so the idea is using these very extreme environments or very unique environments to do these missions and then test technology as well as human behavior, right? And it's really interesting because you'd never know what predicament you will find yourself in when you actually live you know, when you're in space or when you're on the surface of Moon and Mars one day, right? So it's better to have all these skill sets and experience in your pocket, right? So you be, if you're confronted in a particular environment that's unusual that you see or challenges, you've got this set of tools or experiences that you can default to and help you out of a very sticky situation. And a lot of these austere environments is pretty potential life threatening, right? Which is what space is. So it's not space camp, right? It's totally not space camp. It's about how do you survive? How do you thrive? How do you test technology to be able to support you? Because technology is there to support you, not to replace you.
Wonderful, wonderful answer. Students, give the biggest round of applause to our speakers today. Interesting, incredible, wonderful information. So much gratitude from the Mars Society and myself and the students. Your video will be uploaded in the next day or two. This will be, students, if you would like to rewatch, you're getting a lot of clapping hands and thank yous. It will be uploaded on YouTube and linked on the syllabus. Our last talk is today in 2 hours from now. Lee Grant Irons will be speaking again. Thank you so much, Dr. Jewell and Dr. Brown. Much, much appreciated.
Nicole, I want to say to everybody here, I'm actually the director of the Mars Society Los Angeles chapter. So reach out to me if I'll put it, or maybe they can get hold of my email. Nicole, you can give them. And we also will be conducting several analog missions. So if you're interested in joining our missions, or bringing in a project or work on a project, we do offer internships. And if you're qualified for as students for scholarships to do that, then you're more than welcome. So thank you so much for this opportunity. Good luck to everybody.
Thank you so much. Thank you very much. And we'll be speaking again about judging and mentoring as well. Thank you, students. Thank you, speakers. Have a wonderful day. I'll see you guys later. Bye.
Live long and prosper.
Live long and prosper. Bye.